Hello, welcome to this lesson today, 20.2 on cyclic quadrilaterals. If you want to pop today's date and pause the screen while you have a go at the do it now question. So we have a circle and we have 4 points around the edge, points A, B, C and D with a centre marked as O. Angle ABC, so A, B, C, remember with your notation, the letter in the centre is really the angle that you're looking at. So A, B, C, so here is 58 degrees. A part 1 asks you to calculate the size of angle AOC. Now let's assume that they want the smaller side here, so that they want the obtuse angle, so AOC. So from last lesson then we know that the angle subtended from the same 2 points, so the angle at the centre here is double the angle subtended at the circumference. So the angle should be 58 times 2, which is 116 degrees. And then hopefully you stated the reason that the angle at the centre is twice the angle at the circumference. B part 1 asks you to calculate the size of angle ADC. Now hopefully you can see, again, this is an angle at the circumference. The only difference here is, yes, it's subtended from the same 2 points C and A, but these points are in the same segment, the same space as the D, whereas over here they were further down. So all it means is, yes, this is going to be half the angle here, but we need to find this angle that's beneath it. So to start with, you need to do, so if this is 116, it's 360, take away the 116 to find the angle underneath here, and then it will be half of this angle. So angle ADC was 122 for the same reason that the angle at the centre is twice the angle at the circumference, and a little bit later on we'll look at a different way to have done this question. So today we are going to look at what is called a cyclic quadrilateral. So our bronze objective is to know and recap some basic angle facts, and you looked at those last lesson too. Our silver objective is to know and apply the circle theorem relating to a cyclic quadrilateral. And our gold objective is to set out a formal proof using correct notation. So a quadrilateral then, with 4 vertices, 4 corners that lie on the circumference of a circle, is called a cyclic quadrilateral. So the diagram shows one here. So here we have a circle, points A, B, C and D are just 4 random points touching the circumference. Then if you join them to make a quadrilateral, it's called a cyclic quadrilateral. So in this diagram, each point on the circumference is joined to the centre, creating 4 isosceles triangles with base angles of X, Y, W and T. So here we've got 4 points on the edge, it's our cyclic quadrilateral, and then what they've done is they've marked the centre and then created isosceles triangles. Now why are these isosceles triangles? Because basically if this is the centre and we're going a line out to the outside edge, all of these, this is a radius, this is a radius, they are all radii of the circle, which would mean that this is creating an isosceles triangle, so these 2 angles are both the same angle W. We don't know at the moment unless we measured it or we were told. So here, radii, so these 2 angles of Y are the same. These are also radiuses, it's radii, so we've got X and T and T. So that means then all of these angles added together, so X plus Y plus W plus T are equal to 360 degrees, because we know the angles of a quadrilateral add up to 360. This is just formally writing it down. So what we can do then is, because we have 2 of each of the angles, we can take a factor of 2 out and just say that this is X plus Y plus W plus T and 2 lots of is equal to 360. So it's just the algebraic manipulation of this line above. So then, if we divide by the 2 to get rid of it, this would mean that x plus y plus w plus t must be equal to 180 degrees. So if we split this up, so x plus y, why are we doing this? Because you can see x plus y is one corner here, w and t is one corner here. So but x and y and wt are the opposite angles of a cyclic quadrilateral. So x plus t plus y plus w equals 180 just by rearranging the equation. So, and x plus t and y plus w are the other opposite. So this is just a formal proof to prove that the opposite angles of a quadrilateral add up to 360. So, just written down then as a circle theorem, it might be an idea to get this down somewhere, although it is on your summary sheet. So circle theorem 4, the sum of the opposite angles of a cyclic quadrilateral add up to 180 degrees. So in this case it would mean A plus C is equal to 180 degrees and B plus D is also equal to 180 degrees. So if we go back to the do now question, now you know that the opposite angles of a cyclic quadrilateral are equal. Could we have found angle ADC any easier? Well, hopefully you've spotted A, D, C and B. These create the cyclic quadrilateral. So this angle here, the 58 added to the angle at D, which is the ADC which we wanted, should have added up to 180. So is this true? 180 take away 58 certainly does give us 122. So actually we could have found it that way, and our reason could have been that the opposite angles of a cyclic quadrilateral add up to 180 degrees. So this is our circle theorem summary sheet. It might be an idea for you to have printed this off. So which ones have we done so far? So last lesson we looked at the angle in a semicircle always being 90. So if you have a circle with a diameter and then it makes a triangle up to the circumference, this is always a right angle. We also looked at the angles at the circumference being equal, so angles in the same segment. So remember, a segment is just part of a circle cut off by a chord and the rest of the arc of the circumference. So these two, the red and the blue, are in the same segment, so these two are equal to each other. This one is, so 2 points, an angle at the centre is double the angle at the circumference. Now this is drawn in a slightly trickier way, and this is generally the type of exam question that will trick you in an exam, and because it looks like it's not the bog standard angle at the centre. So this one, angle at the centre, is twice the angle at the circumference. This is exactly the same, it's just that they've twisted the points round. So here would be the angle that's at the centre, here's the angle at the circumference. And now we've looked at this one here, that the opposite angles of a cyclic quadrilateral add up to 180 degrees. We will look at the other few next week. So here's an example then. Find the values of x and y in the diagram. So x plus 85 must add up to 180. Therefore, x must be 95. And y plus 108 must equal 180, so y must be 72. Both, remember, if you just list in the reason in an exam, it is because the opposite angles in a cyclic quadrilateral add up to 180 degrees. So now is the exercise. You can have a go at the questions. So if you want to pause the video, and then the answers we can reveal as we go along. Okay. And question 2. Cold call question. So 60 seconds to think and then share. Judy said that every rectangle is cyclic. Prove that she is correct. So now if you think about that, each angle must be 90 degrees, and so opposite angles add up to 180, so hence it's a cyclic quadrilateral. Have a think about the next one. Nathan said that every parallelogram is cyclic. How can you show this is incorrect without having to draw a parallelogram? Well, hopefully if you think about this, you should remember that one pair of opposite angles, if you visualise a parallelogram, a pair of opposite angles are going to be obtuse. That means both of them will be over 90, hence their sum would have been more than 180. So a parallelogram, or not, well, some maybe, but every parallelogram is not cyclic. Question 4. You can pause the video and have a go. Remember to use all of the circle theorems that we've used so far, not just the opposite angles of a cyclic quadrilateral. I'll reveal the answers. And question 5 and 6. And question 7. Question 8, this is more of an in-depth proof question, so if at this point you feel you would just like to go to the Hegarty tasks, that's entirely fine. Question 9. Question 10 is a proof question. And a bit of a hint with this one, if you let angle AED, so this angle here, be X, and then think about everything else in terms of it. So here's the proof that you could have written. And question 11. And then the answers there if you just wanted to print off the exercise and then check through for yourself. Again, here's a summary of the circle theorems, and as I said, next week we will look at the further 3 at the bottom. Good luck with your Hegarty tasks this week.